Okay, welcome to part 2 of our 4.3 homework. Again, hopefully you've seen part 1 if necessary, and on this, hopefully you're not just coming here to get your homework done. That defeats the purpose, and that we will pay the price on tests and quizzes. And when it all comes down to it, that's really what your grade is entirely determined on is tests and quizzes. So, as was mentioned on part 1 video, at this point we should be in the process of learning these. If we have not learned or memorized these guys, we should be able to derive them. If we can't do that or don't feel like doing that, then we need to get that memorized, and in the meantime we may reference these as we're learning them. I gave some hints on the part 1 portion for problems 2 through 8 on some quicker ways, some things that might help memorize these. Obviously there's some similarities along the way. So anyway, at this stage, this is not the entire directions for number 10 and 12, and that's all this video will be about, is number 10 and 12. If you're looking for something else, you need to look at a different place. The full directions say a particle moves along the x-axis. So we're just moving along a horizontal line. Oftentimes that's where I use a squirrel on a wire crossing the road. The wire's taut, squirrels moving back and forth, just to make it a little bit more interesting and something a little more visual I'd be used to seeing. So a particle moves along the x-axis, so that its position at any time where t is greater than or equal to 0 is given as x is t. So this is a position function. And we are then supposed to find the velocity at the given value of t. We want to find the velocity when t is 4, and of course velocity is the first derivative of position. So they're just asking us to find x prime of t, the derivative of this function, or dx dt as the case may be. So sine's derivative is 1 on square root of 1 minus the argument, I should say, squared, times derivative of the argument. So sine's derivative is 1 on square root of 1 minus, I don't know if I said squared here, this is square root of t on 4 squared. That's plain. If this was plain old t, this would be it. This would just be t squared. But now I have to take that times t's derivative, and to do that, I'm going to call this t to the 1/2 on 4, and I still have to find the derivative of that. Okay, so x prime t, or derivative of x with respect to t, dx dt, is, I think I'm going to take care of this into the numerator right here. I'm taking the derivative of this guy. I get 1/2 t to the negative first on 4, or I get 1/8 t to the negative 1/2. That okay? 1/2 t to the negative 1/2 divided by 4, 1/2 divided by 4, 1/8. And that is all on square root of 1 minus square root of t squared t on 16. And maybe we'll do something about cleaning that 16 up when the chance arrives for us. Okay, so from there, if I'm trying to find the derivative, great. I guess I could simplify this. I could move this down to the denominator, or I could just start putting 4 in at this time. Once I'm out of the derivative, the simplifying isn't quite as big of a deal. But we could make this 1 on 8 square root of t times square root of 1 minus t on 16. I don't feel quite as obligated to deal with this. You know, maybe I want to get common denominators and get that fraction out of the radical. But bottom line is, I'm just interested in what's happening when t equals 4. So x prime of t is 1 on 8 root 4 times root 1 minus 4/16. Or 1 on 8 times root 4 is 16 times square root of, this is 1/4 of 3/4, or let's see, 1 on 16, the square root of 1/4 is 1/2, leaving square root of 3 trapped in here, and I get 1/8 root 3 as my velocity. Or if we rationalize that, I know I've run out of room here, and this is a bad thing for me to do, but I'm going to go right in here, velocity. I didn't really try to build a circle around this answer. If I rationalize root 3, I get root 3 on 8 times 3, 24. I probably should organize that a little bit better, but I was running myself out of room. Okay, poor planning, but let's move on. Number 12, same thing. So might want to take a quick peek so we see where we're getting this from. I'm going to be taking the derivative of tangent inverse. And tangent inverse, actually the tangent ones are kind of nice. We don't have any squareds in there. We don't have any absolute values. I'd say tangent cotangent might be the nicest to work with, then sine and cosine, and then the secant cosecant. And again, on the previous class period, we talked about why we have absolute values here. But anyway, tangent inverse derivative is 1/1 plus the argument squared. If the argument's not x, we need to take the derivative of that with respect to x, or in this case, with respect to t. So maybe I'll just write this as dx dt. So our tangent derivative is 1/1 plus the argument squared times the derivative of the argument. Even if it was just plain old t, the derivative of the argument would be 1. It doesn't hurt to do that, but it hurts not to do it quite frequently. So that would be 2t. Or I get 2t on 1 plus t to the 4th. I don't care about simplifying this that much. I care about what's happening when t equals 1. So this is, we could even call it velocity with respect to t. That is the first derivative of our position as we spoke about earlier. So that would be 2 times 1 on 1 plus 1 squared, or 2 on 2. So velocity at t equals 1 is 1. And let's see, what do they give? A particle moves along the x-axis so that its position is at t is greater than or 0 is given at xt. Find the velocity. So this would be, if we were going to use units here, this would be like units per time unit. They didn't give us feet, they didn't give us seconds, anything like that. Our velocity is 1. We don't have a unit right there to put in for our answer, which I assume if it was an AP test, we commonly would. So hope that is helpful. I will continue with the next section of problems, 24, 26, in the next video.